class. All right. Homework one. Homework one, I believe, is due tomorrow. How did you find the problem? Were you able to solve it? I'm actually surprised. That's good. Well, the problem was given as a way to for students to like assess their learning abilities, right? There's no like trick to that problem or anything because we haven't covered the material completely in lecture yet. But the point was that students, I mean, you're going to be engineers in a couple of years, so you'll be learning and working on something new every single day. So if you're faced with something new at your workplace, how would you approach that? How would you learn? Can you use all the resources that that are available to you and able to find a solution? Anyway, my plan is to cover the homework problem on Wednesday, so I'll do that in class. And then, if and there shouldn't be any penalty. So if students lost any points on it, we'll just adjust the credit. Okay. All right. So let's go to our notebook. And let's see, semiconductor. All right. So we stopped here. We looked at the equation. Let's see how it functions. I mean, how it works as a function of temperature. So these plots right here, basically showing us how many carriers are generated or approximate carrier number of carriers that are generated as a function of increasing temperature. So the bottom here, let's say this is 273 degrees. At 273 degrees is of course 0 degrees C. And you can see the majority of the carriers around silicon is below 10 is to 10 is to 10. Gallium arsenide has very few carriers. Germanium by far has the most carriers of all the three. And as the temperature keeps on increasing, at the far end above 300, 400 Kelvin, kind of works into a linear shape and then starts to flatten out. Okay. So the more thermal energy you provide, the more bonds are broken and the more carriers are generated. On the other side, if you go below zero in freezing environments, there are very few carriers that are available intrinsically, right? So this has major implications based on your application, right? So right at the top of the slide, you can see broad classification based on temperature. We have commercial grade electronics, consumer electronics, commercial grade, you have industrial grade, and you have military grade, right? Everything that we use in everyday life, cell phones, tablets, televisions, laptops, computers, they're all consumer grade, right? We might be in a freezing environment, um, below zero. Devices may or may not work. Typically, we would not be outside for very long, right? If it's like freezing environment, you're not going to stay in a freezing environment for hours at a time. But let's say, for instance, if you go, I don't know, skiing perhaps, or really, um, I don't know, underwater scuba diving. But then those devices are function with that. But if you take a normal phone in a very cold environment, you would observe that the device may not function as properly. It may start freezing up, it may start rebooting, just acting out in general. Okay, the reason for that is, of course, temperature has a big effect on semiconductors. All right. If you are in industrial industry, your industry might have, let's say, you might be operating in deep ocean environments, or really hot environments, maybe Antarctica or Arctic. Military grade, even higher extreme ranges of temperatures. So military equipment is required to work in all kinds of temperature and environmental conditions. And so their range is even more extreme than industrial grade. As an example, submarines, outer space, hot deserts, right? So expected to um, design these devices in a way that the temperature effects are minimized. Okay. The entire course that we are dealing with, we are only dealing with consumer electronics, right? We are not concerned with industrial applications or with military grade applications. Okay. All of our discussion is only for consumer based devices. All right. Intrinsic carrier concentrations. Numbers are 10 raised to 10, 10 raised to 9. Those are huge numbers, right? 10 raised to 9 is like a trillion, right? Big or small? Big, right? Carriers are electrons. Thermal energy is imparted to the electrons. Electrons break free. One electron is generated, generates a hole at the same time. So these carry charge, hence they are known as charge carriers. And the generation of these charge carriers is basically due to the thermal energy. Generates charge carriers. Now for, oh yes. So this one, yes, these numbers are for silicon. Numbers for silicon. The chart previously showed us silicon, germanium, and gallium arsenide. Right here. And you can see silicon right around here, very close to 1 into 10 raised to 10. Okay, and that's what it is. 9 into 10 raised to 9, which is about 10 raised to 10. So these charge carriers, again, are generated because the electrons are moving out of their spot, leaving a hole behind. When these electrons break free of their bond, they are free to move around in the crystal structure. If they find an opening anywhere, meaning an empty spot, a hole that is left behind by another electron, that electron could jump into that spot. If it jumps into that spot, that process is said to be recombination. The electron has recombined with the hole, meaning it's left its spot and gone to another spot. Okay. And so when recombination takes place, one negative charge and one positive charge disappears. Okay. Electron moves out of its spot. You have a negative charge just generated and a positive charge that is generated. If that electron is moving around the crystal structure and jumps into another empty spot, it's called recombination. And then recombination gets rid of one negative charge and one positive charge. Electron moves into a spot, it's called recombination. And the amount of time that the electron is free, meaning it's not occupying any spot, is known as the carrier lifetime. How long can the electron behave as a charge carrier? So it is known as the carrier lifetime or the charge carrier lifetime. Okay, carrier lifetime. Okay, so at around 300 Kelvin, which is about room temperature, approximate number of electrons around 10 raised to 10. Okay, 10 raised to 10 electrons per centimeter cube. So the units denote number of electrons per centimeter cube. It always is complex. I don't know how or why, but everything we deal with integrated circuits is microns and nanometers. And These calculations, the equations are always based on centimeter square or centimeter cube. So it seems like a huge number, but a centimeter is about 10 millimeters, and then each millimeter is 1,000 microns, right? So inside each centimeter, we have about 10,000 microns, okay? So if you're converting from centimeters to microns or cubic centimeter, 1 cubic centimeter volume into cubic microns, multiply 10,000, 10,000, 10,000. Otherwise, your equation, your calculation would be incorrect, right? So always keep that in mind, okay? So if we do that conversion, it's approximately equal to 5 free electrons in 1 cubic micron, okay? That doesn't sound so much, especially when you're talking about devices on the order of nanometers. 5 electrons in a micron is not a lot, okay? The point is, these electrons by themselves are not sufficient for conduction, hence it's a semiconductor, okay? All right, so let's take a pause. Let me know if you have any questions. Okay. Yeah. So question being asked is, does time matter for intrinsic carrier generation? Number of electrons? No, not really. Question being asked is, does time matter? The answer is no, because at any given temperature, there are electrons that are constantly moving out of their spot, and they'll be, well, for lack of a better word, they'll be alive and spending their life as a free charge carrier for a certain portion of time. Then they jump into a spot, recombine, and the charge goes away. But to balance that out, it's a natural phenomena that occurs. To balance it out, there's another electron, some other part of the crystal lattice structure that comes up and leaves its spot. So there are constantly electrons being generated, and the constantly electrons that are recombining. And the rate of generation and recombination is always balanced. That's just laws of physics that have been observed. And scientists and researchers have performed experiments to verify all this. On a separate note, like with most engineering fields, there's a specialized niche area for semiconductor fundamentals also. It's a higher level, graduate level course called solid state electronics, where students spend an entire quarter or a semester, deriving and working with these kind of equations at the atomic and the subatomic level. Anyway, going back to our topic. So these electrons are generated solely due to thermal energy. They are inherent to the material. Okay? We do not control or influence except for the temperature, right? So the inherent to the material, hence they are known as intrinsic semiconductors. Intrinsic semiconductors. All right, so intrinsic semiconductors. Carriers are generated only due to thermal energy. Okay, only thermal energy. So by themselves, they are not very useful, right? That's the whole point. Silicon exists, germanium exists. We can create a pure silicon wafer, a pure germanium wafer, but nothing's going to happen. Even if we apply a voltage or an electric field, even if we apply an electric field to that pure silicon, nothing's going to happen. Not unless that electric field is, like, density is huge. So how can we have more electrons in there? Well, one option is what can we do if you want more electrons? Yeah, heat it up more. That would be the other ways, all right? So we can heat it up, right? But that's not always practical. And we'll see in a couple of slides, you'll see the effects of temperature, very high temperature. So you can either have electrons from within the material acquire more thermal, so we apply more thermal energy to the electrons in the material, and so more electrons are released. That's one way. And the other way is if you want to work at a regular room temperature, then we introduce external electrons in there. And so that's the fundamental principle of working with a semiconductor device. We take an external element, either from column 3 or column 5 of the periodic table, and we introduce it into our pure semiconductor material. In this case, the terms pure and impure solely reflect the material itself. If we are talking about material silicon, if we say it's pure silicon, that means there's no other element inside that silicon material. If we say pure germanium, that means there's no other external element inside the germanium material, right? Anything else that is external to it is referred to as an impurity because it does not naturally belong in that silicon material. So if we take an element from column 5 of the periodic table, it has 5 electrons in its outermost orbit, right? If we introduce these 5 electrons in the silicon lattice structure, let's say that atom is going in, displacing a silicon atom and taking its spot, and it bonds with one silicon atom on all 4 sides. Out of those 5 electrons, 4 of them will bond with 4 neighboring silicon atoms, right? Like all silicon atoms do. 4, 4, 4 here, and they form a stable bond, right? So 4 electrons are shared with 4 atoms and leaves behind 1 extra electron. Now that electron is free to move around inside our silicon structure. And thus we have introduced an extra charge carrier at room temperature. Okay, and if we take a look here, this is a column 5 element. It shared 4 electrons on all 4 sides. And this is the extra electron. Okay, that's the extra electron. Everybody with me so far? Okay. And because this is external to the material, the type of semiconductor that is created is known as extrinsic. So we had intrinsic semiconductor, and now we have extrinsic semiconductor. Okay. So extrinsic semiconductors are created due to the introduction of external impurities into our intrinsic material. All right. Okay. So that electron has now broken free of its atom and is now free to move around. So if you apply an electric field, that electron will respond to that electric field because it's not bound to anything. Now, in general, generally speaking, what happens when an atom loses an electron? Absolutely, it becomes ionized. So now we have an ionized atom that has 1 less negative charge, but those 5 electrons are balanced by 5 positive charges in the nucleus. If it lost 1 negative charge, it still has 1 extra positive charge that is bound to the atom. So there are 2 terms that come to that we use to describe this. The first one is that this atom is donating an electron, Hence, it is known as a donor atom. This column 5 element is known as a donor atom because it is donating an electron and is becoming ionized. So it's known as an ionized donor atom. And because it has one extra positive charge, it is a positively charged ionized donor atom. Okay, so donor and positive go together. Okay, the donation refers to the negative charge. It refers to the electron. Obviously, positive charges cannot be donated. Right? You can donate an electron. You can break a proton out of a nucleus, not without. All right, let's take a pause. Think over it. Let me know if you have any questions. Any questions? Yes. So the question being asked is, well, it's not the net charge, it's the charge that's left behind. So the question, it's a good question. So the negative charge is free to move around and conduct, right? That's the whole point. Electron moves, it conducts, it transfers charge, it transfers energy. The positive charge is localized and it's in place in the structure. That positive charge cannot move. It's bound to that atom, right? It's in the nucleus. So it's bound to the atom. But that leads me to a key point. Even though there are a bunch of electrons running free, right? This plethora of electrons, much higher numbers than the intrinsic carriers. So these are like 10 raised to 15, 10 raised to 16. Right? The whole point is we want to control the properties. So we introduce a huge number of atoms in there. So there are 10 raised to 15, 10 raised to 16 electrons that are generated. And we call this as a N-type material because of the negative charges or the free negative charges. So it's known as an N-type material. The key point here is, though, overall, it is electrically charged neutral. Because even though the electrons are free to move around in the lattice structure, they're all, each and every single negatively charged electron is balanced by a positive charge in the atom. So even though it's an N-type material, which means it has free electrons for conduction, the overall electrical charge is neutral. Yes. Donor atom would not have a hole. So intrinsically generated carriers would have a hole because they're breaking their covalent bonds and they're leaving. But the donor atom has an extra electron. It's not bonded to anything. So when we insert this atom in the silicon structure, 4 of these atoms bond with 4 neighboring silicon atoms. The fifth electron never bonds with anything. It's just free. It's just free to move around. And when it acquires sufficient energy, it can break free of its bond and it's just going. No. So, okay, I understand the question now. So the question being asked is, the 5th electron, we are saying it's free to move around, right? So if it's free to move around, it's creating a hole in there, right? That's what you're asking. So it's creating a hole in there. But the point is that it's not bonded to anything in the first place. There's no covalent bond. Because we introduced this, the covalent bonds are created here. Right? These are the covalent bonds, the ones that are marked in red. Those are the covalent bonds. If it's an atom by itself, there's no bond. And so when it leaves, it's just freely conducting. There is no corresponding hole that is created. It's just free electrons. Yes.
I think holes don't cancel the electrons, and it's just the nucleus that cancels.
Yes, the nucleus of that donor atom has a positive charge, and so that balances out that charge of the electron. Does that make sense to everyone? Okay. All right. So that's N-type material. So let's look at what happens when you have column 3 elements. So you have column 3 element implanted in there. Okay. All right, column 3 element implanted in there. 3 of the electrons in the outermost orbit will bond with 3 of the other silicon atoms. It will leave an empty spot right there, empty spot. And when it leaves an empty spot, an electron from somewhere else with another atom is free to jump into that empty spot. And when an electron jumps into that empty spot, again, that empty spot does not have any charge associated with it. So column 3 elements. This is kind of an extension of the question that was asked earlier. So if column 3 elements have 3 electrons, right? It has 3 electrons. So 3 electrons will bond to 1 silicon atom each. There's one bond that is not formed, but it's not broken. It was never formed in the first place. So there is no positive charge associated with the empty spot. But because it's an empty spot, an electron from some other part of the lattice structure from other silicon atoms can jump into that empty spot. And it happens. So when it jumps into that empty spot, it's going to leave behind a hole in its spot. So here in the second illustration, empty spot is filled. Okay, empty spot is filled. And that it's, let me see. There's not enough space, but I'm going to draw that arrow right here. So you see that one Q right there is an electron that moved out from here and jumped into that empty spot. Okay, and because it jumped out of its spot, electron left. Creates hole. Okay, so again, column 3 elements have a empty spot because it only has 3 electrons. So some other electrons from some other part of the structure will jump into those spots. And when they leave their bonds and jump into those spots, they are going to leave behind positively charged holes. So there is an excess of positively charged holes that are created. And hence, these are known as p-type semiconductors. This is known as a p-type material. So column 5 creates n-type material. Column 3 creates p-type material. N and p-type. Okay. The most common, oh, this is, by the way, column 5 have an extra electron, they are donating. Column 3 have only 3 electrons, so they are receiving or accepting electrons. And because they're accepting electrons, they are known as acceptor atoms. And because they're accepting an extra electron, that electron is not balanced out by the nucleus. The nucleus has 3 positive charges, 3 electrons. You have 1 extra charge. So it's a negatively charged ionized acceptor atom. So donor and positive go together, and acceptor and negative go together. Okay. Acceptor atoms are ionized negative, negatively charged ionized atoms, and donor atoms are positively charged ionized atoms. The most common ones are I mean, the most common elements used as impurities are phosphorus and boron. Okay, phosphorus and boron. Phosphorus, phosphorus and arsenic are from column 5, so they create N-type material. And boron creates P-type. Okay. The process of introducing these impurities into the material is known as doping. The impurities are labeled or called as dopants. And the semiconductor that has received these impurities, known as doped semiconductors. Doped semiconductors. Here at Cal Poly in the clean room course, we use phosphorus and boron both to create a P and N-type material. Yes, question being asked is, are these extrinsic semiconductors? The answer is yes. Because we're introducing external impurities, so these are extrinsic or doped semiconductor. Okay, a couple of minutes left. Let's look at this. Yes. No. Holes would also be, so the question being asked is, are holes in the valence band and electrons in the conduction band? The answer is not quite, no. Both holes and electrons are in the conduction band because they are free to move around. Obviously, the actual phenomena that's taking place is that electrons are moving into spots, leaving behind holes. But again, recall the previous lecture where I stated we treat a hole as a particle in its own right with a positive charge. Okay. All right. So intrinsic semiconductors obviously by themselves are not useful. If we look at intrinsic semiconductor right here at temperatures that are lower than 500 Kelvin, the number of intrinsic carriers may be around 10 raised to 10 for silicon, right? 9 into 10 raised to 9 into 10 raised to 9. I always like to say it's 10 raised to 10. Gallium arsenide is lower, germanium is a little higher, but it's not sufficient to create a conductor or a resistor out of it. Okay, so we introduce extra charge carriers in there, which are in the range of 10 raised to 16, 10 raised to 17, 18, 19, 20. But at higher temperatures, what happens is when you go much higher, we are out of time. So if you have to leave, you can leave. I'm just going to wrap up here. At higher temperatures, more and more bonds in the intrinsic material are being broken. So more electrons are being generated. More electron hole pairs are being generated. So at very high temperatures, those intrinsically generated charge carriers are going to number much higher than the extrinsic dopants that we've introduced. So originally at room temperature, let's say your intrinsic generation is 10 raised to 10. We introduce 10 raised to 16 external impurities in there. As the temperature increases, that 10 raised to 10 goes to 11, 12, 13, 14, 15, 16. And at some point, which is basically indicated right here, is going to increase beyond the extrinsic impurity levels. And so at higher temperatures, it's intrinsic charge carriers that dominate conduction. Okay, and that's the effect of temperature. And that's what happens here. Okay, just one more thing about notations. Ni is basically number of charge carriers or number of carriers that are generated, and I stands for intrinsic. Na is the number of acceptor atoms, and Nd is the number of donor atoms. All right. We'll end class here today and we'll pick up here again on Wednesday.